Hi, my name is Kaylee Garcia, and I did my dynamics project on finding the angular velocity of a thin hoop going down an incline, starting from rest. You can see this in the following video. Go. As you can see, I use As you can see, I used duct tape as my thin hoop, and according to As you can see, I used duct tape as my thin hoop, starting from rest, and rolled it down a smooth incline. Then I calculated the angular velocity at the horizontal plane, which in this case will be point B. From the basic definition of radius of gyration, for a thin hoop, the radius of gyration is just equal to the radius itself. So my theoretical calculations are as follows. If this is the setup of the incline, this is the duct tape, this is the incline, and this is the chair. The incline was 18.31 inches off of the ground and 30 inches from the edge of the chair. The duct tape started at point A at rest and had a radius of 1.5 inches. Then my goal is to measure the angular velocity at point B. So for this calculation, I use the conservation of energy. This is because the duct tape begins with the potential energy and it starts at rest. Then it ends with kinetic energy, but potential energy is 0. So I used T1 plus V1 equals T2 plus V2. Since kinetic energy is 0 at rest, T1 is equal to 0. Then potential energy is equal to mass times acceleration due to gravity times height. And that's equal to 1/2 the moment of inertia times the angular velocity squared. In this case, moment of inertia is mk squared, where k is the radius of gyration. As I said before, though, the radius of gyration for a thin hoop specifically is equal to r. So then you also add 1/2 m v velocity at g squared. And so according to the equation, the velocity is equal to r cross w. So I ended up plugging r cross w into here. So as you can see, I took the mass of the duct tape before beginning, and I got 1.75 ounces. I then converted this to grams and got 49.6116 grams. So this is the mass here, and then acceleration due to gravity, 9.81 meters per second, and then the height, which was 18.31 inches, which I converted to meters by multiplying by 0.0254. And then is equal to 1/2 the mass, again 1.75 ounces times 28.3 grams to convert it to grams. Then the radius of gyration, which I said was the same as the radius, so I converted that to meters. Then omega squared plus 1/2 velocity squared. And so, as I said before, velocity is r cross w. So here's the radius converted, and w squared. I ran out of room there. And I just went through the calculation and solved for w, and got 56.04 radians per second. So these were my theoretical calculations. For my actual calculations, I used the video and imported it into an application called Tracker. Tracker allows you to import a video and then go frame by frame, placing manually a series of dots, and then it graphs it for you. So it's a bit hard to see, but this is a frame of the video, and there are arrows down here showing the velocity vectors, and there's a path in which the duct tape travels. Online it's green, it's red, so you can see that. Then it also formed it into a table, and it also graphed it for me. This is the shape of a parabola. So what I did was, since I'm not given angular velocity, I used the equation v equals r cross w, and then angular velocity equals velocity over radius. So since we're only given the velocity in the distance in x and the distance in y, as you can see here, we have time in seconds, x in meters, and y in meters. I use the final equation v equals vx squared plus vy. So to find vx squared, I tried using the final point, which was for x, this one here, minus the initial point. As you can see, they're negative, but that's simply because the axis is in the opposite direction, but we'll regard those as positive. So final minus initial over time, final minus initial. And I did the same thing for y, final minus initial over time, final minus initial. So that's these calculations here. So for v of x, I got 0.107 meters per second, and for v of y, I got 0.0596 meters per second. Then I squared those and took the square root of it and got 0.122 meters per second. Then I plugged that into the equation, divided it by r, which was 0.0381, and which is converted from 1.5 inches. And I got 3.2 radians per second, which, as you recall from the theoretical calculation, I had 56 radians per second, so that is definitely off. Then I tried thinking that the velocity that I measured is assuming constant velocity. So in this case, it was not constant velocity since it started slow at first and it started speeding up toward the end. So then what I did was I just took the last 2 points of x and y. So I did, for v of x, I did final minus the second to last point, and same for time, final minus the second to last point, and same for y, final minus the second to last point over these 2 times. So doing the same calculations here and here, vx and vy, and then solving for v, and then plugging into w equals v over r, I got 7.24 radians per second, which is still drastically off comparison to 56 radians per second. So I think the problem was that this application did not allow for the actual measurement of the turning of the duct tape. So what would have been ideal was for me to set a constant axis along here as a reference, and then if I had a marker, let's say on the top point of the duct tape at rest, then every frame I would just mark that marker. And so that would note the rotational movement of the duct tape. And so hopefully it would have given me rotational velocity. Yeah. But it did not, because the program isn't that advanced. So my guess is that the best way to know the accurate angular velocity is just to go through the theoretical calculations using the equation t1 plus v1 equals t2 plus v2, making t1 equals 1/2 I to b squared plus 1/2 mv squared, and then V equals mgh. So that is all. Thank you very much.